Okay, now it gets really interesting. This is where the fun part of conditional probability comes in. So we're going to do some tree diagrams, and a tree diagram, as you may remember, helps you think through conditional probability so you can see the different sequences or events of the past as they look on the tree. Making a tree diagram for these situations is the picture. So just to go back, you did these in middle school. You would create a tree diagram here, and here's me creating a tree diagram for different types of bread. So we're ordering box sandwiches for our club social, and we're choosing between wheat and panini bread, and then from turkey, ham, or vegetarian filling. So we make a tree diagram. So you can see that for each choice of bread, I have the choices of filling. So you've done tree diagrams before, and you actually like them. So let's go ahead and take a look at them with probabilities in them. So here's an interesting tree diagram. Let's see, it looks like we've got alcohol consumption, binge drinking, moderate drinking, and abstaining. And then accident or no accident. Interestingly, okay, so if they abstained, apparently they didn't have an accident. Well, because honestly, the probability of you having an accident is pretty low. But if you binge drink, the probabilities of you having an accident go up quite a bit to 17%. If you have moderate drinking, interesting, about half the probability of binge drinking. So be careful with that. And then the probability, there are lucky people who don't have accidents because they were just lucky even though they were drinking. So if you look at here on the right side, this is the probability of taking a random person and that they were binge drinking. I guess these were people at a bar or something, and they have an accident. So 7.5%, that's kind of high. The probability that someone binge drank and they didn't have an accident. The probability someone drank moderately and they had an accident. The probability someone drank moderately and they didn't have an accident. The probability of someone who had abstained and didn't have an accident. And the probability of someone who did have an accident, sorry. And the probability of someone who abstained and didn't have an accident. So if you multiply these numbers, 0.444 times 0.17, you can go ahead and get these values. So you can, because these numbers here change, it's not a simple, 0.44 times what the typical accident rate was. It's 0.44 times the probability of accident given that you binge drank. So those probabilities are changing based on this initial condition here. All right, so when we reverse the condition, basically Bayes' rule, and we want to know the probability of A given B, but we only know the probability of A and probability of B and B given A. Suppose we want to know that, we can basically use these formulas right here. So it's a lot easier when I go look at the tree. So first of all, we're going to consider an example. In April 2003, Science magazine reported on a new computer-based test for ovarian cancer. It examines a blood sample for the presence of certain patterns of proteins. Ovarian cancer, though dangerous, is very rare, afflicting only 1 out of every 5,000 women. That probably is still pretty high for that poor woman. The test is highly sensitive, able to correctly detect the presence of ovarian cancer in 99.97% of women who had the disease. However, it is unlikely to be used as a screening test, and you're probably going, why? Let me go ahead and put this in here. So, we say that only 1 in 5,000 women have ovarian cancer. So that's 2 out of 10,000. So there's 0.0002. That's the probability that a woman has ovarian cancer. And here's the probability a woman doesn't have ovarian cancer. Makes sense? They should add up to 1. So I'm constructing this tree diagram. Now, we told you the test is 99.97% accurate in terms of if a person has ovarian cancer, it will tell you that person has ovarian cancer. Now, you will have a very tiny percentage who have ovarian cancer, and the test will miss. So it's the smaller this number is, the better. So based on this looks like a great test. All right, here's the twist. In general, the population, the test also gave false positives for 5% of the population. And you're probably thinking, well, that's still pretty good. It's only 5%. So here we have 0.05. So for 95% of the women who don't have cancer, it's going to give them the right result. It's only 5%. And what does that, I mean, we should go ahead and use it as a screening tool. So let's go ahead and actually calculate some probabilities that a woman who tests positive on this screening tool actually has cancer. So this is what I'm trying to find. The probability the person has cancer given they test positive. And there's my old rule. Probability of cancer given and positive over probability of testing positive. So you can see they did some multiplications, and I went ahead and did the same thing. Probability of cancer and testing positive is the product of these two, which looks like it's really tiny, 0.0001999. All right, almost the same as 0.0002, right? So, and then I need to know the probability that, so I'm trying to find the probability of positive. So now I need to look at this testing positive and this testing positive and calculate it. So the probability that a woman doesn't have cancer and tests positive, I just did this one first for some reason, is the product of these two numbers right here. And I got 0.049999, which is a lot like 5% because it's so rare. This is almost 0 and this is almost 1. Okay, what about the probability a woman has cancer, a test positive? Well, then I just add these two test positive answers together, and I've got 0.05018999. So only about 5% of my population is going to test positive. So far, so good. But what's the probability that a woman who tests positive, remember, given they tested positive, what is the probability they have cancer? Well, I put in the probability of cancer and positive on top, the probability of positive on bottom, and it's only 0.4%. So the problem is I'm going to get all these positive test results, and less than 1% of these women who have positive test results will actually have cancer. So it's going to really, this is going to happen anytime you have these big differences in numbers where things are almost 0 and things are almost 1. So, and this also brings up, we'll go over class, how about other types of tests, like when we have the Olympics and they test for steroids? We tend to assume that the athlete is automatically guilty if they have a positive drug test. How does that work out? So, let's go ahead and go over what can go wrong with probability for this chapter. Don't use a simple probability rule where the general rule is appropriate. You can actually use a general rule all the time, and the simple probability rule will pop out when they are independent, okay? Don't find probabilities for samples drawn without replacement as if they had been drawn with replacement. Remember, pay attention. Are the probabilities changing? And don't reverse conditioning naively. So basically, if we look at that cancer test, it's so easy to think that, oh, it's so great. But when you go and do the actual calculations, it's not what you think it is. And don't confuse disjoint with independent. Remember, disjoint means mutually exclusive. That's like getting a king or a queen. King and queen is disjoint. Independent would be drawing a card and rolling a die. They don't depend on each other.